All right, good morning. Can you all hear me?
Yes.
All right, thank you. Okay. So a couple things before I get started. The exam, I graded all the exam. The average was a little bit lower than I expected, but I mean, this is the first test. And this is part of the reason why I'm grading on the curve. So technically, if I was grading on a curve, anything above 84 would have been an A. So, and we had several students above that. So anyway, we'll see. I think as a class we did okay. I mean, on this first test. So I know that it doesn't look like a good average. We don't have a large class, so that we had a large spread in the scores, and so that can be a reason why the average is lower than I would expect it. With my other class, I have a bigger, it's a bigger group, and with a bigger group, the average is a little bit higher. I think that I would attribute the lower average to a smaller class, okay? Because then you have a bigger spread in the scores. So I will try to create a video as soon as I can with the solutions to the exam. I should say one thing on problem 2, those of you who did problem 2, really what I looked for, and I should have phrased that question better. What I looked for is, did you apply Gauss's law in the first part? The second part wasn't a problem. The first part, I looked for, did you apply Gauss's law and did you integrate the charge? So one of the big, I think, really issues that I noticed on this exam was that when you are given a charge distribution, let's say rho equals A r to the fourth, and you wanted to calculate the total charge enclosed or the total charge of the system, you got to integrate that. That's not constant. One of the things, and it's hard to unlearn this because you see it when you're in high school. You learn that density is something over volume. And this is only true if this is constant over the whole volume. And a lot of folks got to remember that. Okay, this is only true if this is constant over the volume. And so what a lot of people did is they took this to multiply by the volume. You can't do that. Okay, you could only do it if rho is constant. That's why I gave you exercise 9 on homework 1. So that was one of the big things I noticed. And in problem number 5 looked like an imposing problem. But in part A, and a lot of people didn't read part A correctly. Part A said find the total charge. That's all I wanted you to do. Okay? And some people started using Gauss's law, which you don't need to use Gauss's law because it wasn't asking for an electric field. And then in part B, it said, what is the force on this charge due to a plane? So you have a plane here, and you have a charge here. Remember, when you're outside of the sphere, it acts like a point charge. And so F is Q times E. The electric field is the field due to a plane, and Q is the answer to part A. This was a conceptual question. The system looked imposing, but it was really a conceptual question. Part C was a little bit harder because you actually had to in order to find the speed of the object, you had to calculate potential difference. So in part C, you had to use this integral. Okay. Now, to me, the hardest problems were part number 2, B, and 5C. To me, those were the hardest problems on the exam. But go over the exam, look over the mistakes you had made. And really what you want to do is look over the mistakes you had made before you actually see an answer key. Can you now work through those problems? Okay. And don't worry if you make an algebra error, but can you approach the problems now? Okay, that's really what you want to look at. And you know, on an exam, I don't grade a lot on the math. It's because this is more of a physics class. That's why I tend to be more conceptual in the questions I give as opposed to very mathematical. When you take junior level courses, you'll get more mathematical problems. If you have any questions regarding the exam, please don't hesitate to ask me. And again, because of the fact that I try to create exams that are hard to Google, it's hard to gauge how difficult the problems could be. Like number 5 is a problem I've given before anyway, but because that one's very conceptual. But like number 2 was one that was a little bit new. Okay, so that to me was a harder problem. All right. Questions on that? Okay. So there's a worksheet on Canvas for this module. It's called the Capacitor Worksheet. And I want you to do this worksheet and turn it in next week. It's not a long worksheet. It's not like the Gauss's Law worksheet. But it basically it has you look at the electric field in between the plates of the capacitor. It makes you plot some graphs. It's just an exercise into helping you to better understand basically what's going on in between the plates of a capacitor. And when you do this, look in your textbook because there's similar stuff in your textbook on this. Okay? So please look at your textbook. And make sure you study and understand the problem. Oh yeah, the first problem on the exam was actually in the PowerPoint notes. I phrased it differently. I gave you different parameters, but the first problem in the exam was in the class notes that I played on the video. Okay, so anyway, this is due next Friday. Exam 2 is on the 16th. And then homework 4 is due tonight. So, for lab on Monday, I'm going to use some time to answer questions you may have on homework 5. That's it's a short homework assignment. A lot of the problems on homework 5 are conceptual in nature. And the calculations aren't very long either. So you should be able to whip through that assignment. There's actually a bunch of multiple choice questions on it. Okay. But I can use Monday to answer questions you may have on the homework so that you can get through the assignment. But it shouldn't be a hard assignment. It's the homework 6, which should be a little meaty, a lot more mathematical because you're going to be solving circuit problems. Okay. So we will be ahead of the game. I mean, next week, I will already be starting at the next unit. And actually, I have to do that. And the reason why I have to be ahead of the game is because we're missing a Friday in November. And so I do have to stay 1 week ahead, almost 1 week ahead in the lectures. Otherwise, we'll be in trouble. Okay, we won't cover the material we need to cover. Questions?
Yeah, Professor?
Yes.
Can you say which chapters will be on the second exam?
Yeah, so exam 2 will be chapters 26 through 28.
Okay, thank you.
What's nice about this course is all the all the unit exams are 3 chapters. Everything breaks down so nicely in this course. So the exam 3 will be 29, 30, and 31. Okay. Other questions? Oh yeah, regarding the exam, I'm hoping on the next exam you can all submit, I can get more people to submit the exam onto Canvas. It makes it much easier to grade. It is much more difficult to grade your PDF without the Canvas speed grader that I use. And even that speed grader is not that great either. Okay. So anyway, you might have to practice uploading stuff. I will have another scanning assignment to see how fast you can upload an assignment. Okay, it'll kind of as a homework assignment, it'll be really quick. I just want to see, I just want you to get good at it so that when you take the exam, we have less problems. Okay. So last time sometimes when I get started in class, I forget to do some demos. So I have a demo that I wanted to do. It's actually a simple demo which describes really how electrons go through a wire. So I hope you can see this. Pretend this is a wire, okay? This is a mechanical model for the electrons going through a wire. And you guys can all see the nails on here. These represent the location of the atoms. Now, what I can't do here is these nails here are fixed in place, but in reality, these atoms are vibrating. Okay, these atoms are vibrating. And so what I have here is the electrons, which are this is a bunch of steel balls. And I'm going to send the electrons through the wire. So you heard all those collisions, right? You can hear the collisions. Maybe you might not be able to see the balls bouncing through, off the nails. But this is an example of what the electrons are doing in a wire. And as they collide, they do dump some of their energy into the material. That's why wires get hot when you run a lot of current. Okay. Now the only difference is that in this model, the atoms don't get stuck. Okay, in this model they get stuck. In reality, they don't. Okay. And the other thing that's true is that the electrons are waves. So you have to use a quantum mechanical model to actually describe what's going on here. You have to take into account that the atoms are vibrating. You also have to take into account the electron-electron interactions. So in reality, it's a very complicated problem. But that simple model that we talked about really is nice because it allows us to see kind of where Ohm's law comes from. I mean, we can see the basis for Ohm's law in that simple model. But a real model that can predict measured quantities more accurately requires a quantum mechanical description. Okay, so let me get rid of my stuck electrons. And let me move my model here. So what I want to do today is talk about DC circuits. I want to talk about direct current circuits. So I guess the first thing to discuss is, what does DC mean? Does anybody want to chime in and say what DC means? Direct current, what does that mean? Well, direct current, what that means is you have a charge flowing in one direction. Okay, it means the charge is flowing in one direction. The current doesn't have to be constant. Granted, the demo, not the demos, but the experiments we do, the problems we do, involve batteries, and the current is constant. But in reality, as long as the current is moving in one direction, we call that DC current. Okay. Now the demo, and I didn't post the demo to the class, but I posted it on Discord. Oops, 1 second. Okay, so I posted on Discord. There's a demo where Tyler created a little video of using AC current. He ran some AC current through a hot dog, and you get to watch the hot dog cook. Whether we talk about AC current or DC current in this chapter, especially in regards to Ohm's law, it's really not going to make a difference, but the focus here will be on DC current. Okay. All right. Oops. So I want to start by talking about circuits where resistors are in series, and then circuits in which resistors are in parallel. Now remember, a resistor is a device that limits current. Okay, so a resistor basically limits current. Another way, and you can also use it to produce a voltage drop that you want. Okay, and then you can hook up a load to it. So there's a couple applications for this. Now, so what is a resistor? I mean, while you're using it in Ohm's Law lab, they come in various sizes. I mean, the ones you're going to be using are tiny, right? They're really small. And they're designed to obey Ohm's law as long as you do not put too much power into them. Okay? If you try to run too much current through them, what will happen is they will heat up. They will not obey Ohm's law anymore. And in fact, if you put too much current through them, you will start seeing them smoke and melt. Okay? When we do the Ohm's Law lab on campus, sometimes you put a resistor that's nice and small, so that when the student turns up the voltage, their Ohm's Law graph starts doing this. Actually, wrong way. And that tells them right away they did something wrong. I can't do that since we're doing this. You're doing the lab at home. Number one is the safety issues. Okay, so. If you put too much current in a resistor, you're going to start making it get real hot, and then it won't be Ohm's law. So these devices we call resistors are generally designed so that they work within the limitations of Ohm's law. Okay, and they're rated according to how much power they can dissipate. Quarter watt, half watt, etc. And you can kind of tell the difference between a quarter watt and a half watt resistor basically on their size. There's no label on the resistor itself. Okay, you just got to go by their size. Or if it's in the packaging will tell you. Okay. All right. So suppose I have two resistors in series. And really, I can apply this to a light bulb, even though a light bulb doesn't obey Ohm's law. What I'm going to do here, I can apply to a light bulb. Because remember, a light bulb doesn't obey Ohm's law, but you can still define resistance for the light bulb. All right. And my line of reasoning here is going to be the same as when I did capacitors and in series and parallel. So let me draw a circuit with two resistors in series. R1, and let's make sure that the two resistors are not equal in value. And this is our power supply voltage. So if I trace the electrons going through my circuit, or I guess I got to go this way. This is the path of the electrons, right? But by definition, current is actually the other direction. Okay. Because I is NQV times A. Okay. Both of these are going, let's say, if that way is negative, both of these, this is negative, that's negative, that makes this whole thing positive. So positively charged, if we thought of as positively charged particles going through here, the current would be, we would say I is this way. This is the electron flow. This is positive flow of charge. But either way, the current is defined to be, the current is clockwise in this circuit. Okay? Even though the electrons are going the other way. The current's that way. And since J is sigma E, the current density is in that direction. Then this is the direction of decreasing potential, because that's what the electric field's this way. These are in the same direction. That's a positive number. So this is the direction of decreasing V. Okay, because the electric field points in the direction of decreasing V. Okay, there's only one path for the electrons to go through, which means that the amount of charge going through here per unit time has to be equal to the amount of charge going through here per unit time. So I can readily say that the current going through our resistance 1 has to be equal to the current going through resistor 2, because there's only one path going through this closed loop. Okay, remember, a closed path is considered a loop. It's called a loop, sorry. Now what else do we know? Well, when charge flows through a resistor, the voltage will drop. So let's pretend this is 3 volts. This is 0 volts. This is 3 volts. This has got to be some sort of intermediate voltage, because when current goes through this resistor, the voltage drops. From Ohm's law, delta V is I times R. And then this is 0. Okay, so what's delta V? So if I'm going this way, and since I'm writing my delta V as a positive number, I'm going to take this voltage drop, 3 minus VI, and I'll add it to this voltage drop, VI minus 0. You'll see that the delta V is 3. If I'm writing this as a positive number. So that means then that delta V R1 plus delta V R2 equals delta V. But from Ohm's law, I know that delta V is I times R. So then I could go into this equation and say, oh, well, this is I times R1, and let me call this I, plus I times R2, which equals the battery voltage. Now what I want to do is replace those two resistors with the equivalent one, meaning I want to replace those two resistors so I can get the same total current through my circuit. I'm going to replace these two with a single one, and so this is going to be equal to the current times R equivalent, or R total, whatever you want to call it. So I can solve for R equivalent. You can see that the I's cancel, right? You have an I here, an I here, and an I here, so the I's cancel. And so R equivalent is R1 plus R2. So I want to write something down, because I want to show you the difference between capacitors and resistors. Okay, I need to spray here. 1 second. All right, so remember for capacitors, in series, well, for resistors, Okay, notice the difference between the equations. And then, of course, we're going to do parallel too. We'll do that in a second. So are we all okay with this derivation? And I have the whole derivation in your notes. Okay. I have that I have the derivation there in your notes. Okay. So basically what we're doing is replacing these two with an equivalent one. So the rules I use is the current between, through those two has got to be the same, and the sum of these voltage drops has to be equal to the voltage drop across the battery or power supply. Now, one thing you want to notice is that if I actually go around my circuit, if I go clockwise around my circuit and I sum the actual voltage drops, taking into account signs, that this is 0. In other words, if I go from here to here, if I sum clockwise, I go from 0 to 3 volts. That's a gain, right? If I sum my voltages clockwise, I go from 0 to 3, which is a positive number, positive 3. Then I go from 3 to something intermediate, and then something intermediate to 0. That's a voltage drop. So I go up 3, and then when I go from here to here, I go down 3. When I add them all up, I get 0. That's true for any loop in any circuit. And this idea is not going to be of a lot of use in series circuits, but it will be of a lot of use when we do the more complex circuits, which we'll do later today. This is called Kirchhoff's loop rule. It's also called Kirchhoff's voltage rule or Kirchhoff's voltage law. And the reason why this is true is because the electric field is conservative. That if you integrate the electric field around this closed path, you got to get 0. So this is a consequence of the fact that the field is conservative. This is basically conservation of energy. Okay, this is conservation of energy. Because if you multiply that equation you see on the screen times Q, you're looking at the work done around the closed path is 0. Make sense? Okay. You guys are quiet today. Now let's look at the case where the resistors are in parallel. Again, these can be light bulbs, or they can just be some element that you put in a circuit to limit current. So let me draw my circuit. And if you have any questions, don't hesitate to ask. So here we go. Let's draw this. So these resistors are in parallel. So let's just put some numbers in just for fun. Let's say this is a 3-volt battery and I ground one terminal of the battery. And I go through different parts of the circuit. Remember, we're going to assume that the resistors have no resistance, or their resistance is negligible. So the voltage drop from here to here is really too hard to measure. So I'm still going to call this 3 volts. I'll still call this 3 volts. That means this point is 3 volts. And so are these 2 points. And of course I could do the same thing on the other side. So you can see that the voltage drops from 3 to 0 here, from 3 to 0 here. So the voltage drop across each resistor, maybe I'll use a different color. It's got to be the same. Right, because it goes from 3 to 0 here and from 3 to 0 here. And they're connected to the battery. So this is different. In series, they added, right? Here, in parallel, they're equal to each other. What about the current? Well, think of the electrons. Think of the current. Think of water flowing through a pipe. They reach this point. Now they have the water has a decision to make, or the electrons have a decision to make. Some can go this way. Some can go this way. If this is I can call this I1, and this is, I could call that I2. So the current splits. Just like when your water is flowing through a pipe and it hits a T, some water can go one way and the other water can go the other way. And so I can say then that the total current has got to be equal to I1 plus I2. It can't go anywhere else. And then the same thing here. I1 goes here. I2 goes here. And then all the current comes out. Whatever enters this point has to be equal to whatever leaves this point. You can define whatever enters this point as positive and whatever leaves this point as negative. There's different ways of designating it. But if you do that, then the sum of them is going to be 0. And that's conservation of charge. Okay. Well, we're going to use Ohm's law here. I is basically delta V over R1. And what I want to do is replace these 2 resistors with a single one that gives me the same result. So this is going to be the battery voltage over R equivalent. And you can see that the delta V's will cancel. And so this is how resistors add in parallel. So let me write down the series one. And then the parallel one. Notice the difference in the forms of the equation. Students get mixed up between series and parallel depending on whether you're dealing with capacitors or resistors. Okay, and I write this down so you make a note of that. Okay, that's an important difference. By the way, if you don't remember these equations, you should learn how to derive them because they're not that hard to derive. Because if you learn how to derive them, you don't have to memorize anything. All right, if you remember the principles, you can come up with this no problem. There's less memorizing for you to do. So when we're doing resistors in parallel, and again I have the derivation in your notes. So let me skip that because I just did it. But when you have resistors in parallel, the sum of the currents in any junction or node equals 0. What that means is whatever, if you take whatever goes in and add it to whatever comes out, that's equal to 0. You can say whatever goes into here is positive and whatever goes out of here is negative. Or you can say whatever goes in here has to be equal to whatever comes out. Right? Because if I write this equation, if I put these two on the opposite side of the equation, These are the same thing, right? All I did is rearrange the equation. So some folks write it as the sum of the currents equals 0, which sometimes is confusing. What is the same thing as this? All we did is take these two guys and put them to the other side of the equation. This is another one of Kirchhoff's laws. It's Kirchhoff's junction rule, Kirchhoff's current rule, or Kirchhoff's current law. There's different names for it. Basically, the sum of the currents equals 0. So you can define whatever goes into a node as positive, whatever leaves is negative. Or you can write it this way, which I tend to prefer to do. Okay. So here's a review of our equations for series and parallel. So I will do an example, and I'm not going to do one that's either series or parallel. You guys are, this is physics 210, so I'm going to start with a more complicated one. And the example I will do is going to be very similar to the capacitor problem I did. So I'm going to do a demo here, but I need your input. I need your help, okay? So I want to see what you're thinking. It's more of an interactive demo. So I have let me move back. I have to adjust the camera, I guess. Hold on a second. Otherwise you can't see. Let me adjust the camera. Okay. So I need you guys to participate here, okay? 3 light bulbs.
Okay.
1, 2, 3. Okay?
Okay.
25 watt, 60 watt. I couldn't find 100 watt, so this is 200 watt bulb. So I have these connected in series. I'm going to flip the switch. Which one's going to be the brightest?
Wouldn't they all be the same?
That's a good question.
Well, because it's the same current flowing through. Oh, wait, no.
Go ahead, continue. I mean, you have the right thought process.
Well, because the same charge is flowing through them, isn't it? If they all have the same resistance.
Yeah, but are they? This is 25. This is 60.
Oh, but there's voltage drop across them. Okay, yeah. So it would be the brightest would be the. Okay, now you're just confusing me.
Which one will be the brightest?
I don't know.
Well, which one will have the biggest voltage drop across it?
Well, wouldn't it be the 200 watt?
Does that one have the biggest resistance?
Yes, maybe.
Well, hold on a second. Hold on a second. These are all 120 watt, 120 volt bulbs. Let me make my room dimmer here. Okay, so these are 120 volt bulbs. Remember that power is delta V squared over R. And I asked this question last week. If you want higher power, your resistance has to be lower, right?
Oh, yeah, okay.
So which one then has the biggest resistance?
The first one.
The first one. So if I turn it on, you'll see. In fact, you can't even see, I mean, that one's, you can't see that one at all, right? It's very dim. Can you guys see the middle one? It's actually kind of lit. The filament's barely on.
A little bit, yeah.
Yeah, a little teeny bit.
You can see a little bit, okay, because I'm kind of far away. It's easier when it's live in class. But yeah, that one looks like it's dead. How do I know that that bulb is not dead?
Because otherwise, none of them would be on.
I'm sorry?
Otherwise, none of them would be on.
Yeah, none of them would be on, right? Because it would be the same thing as if I took this out, right? If that bulb was dead, it would be the same thing as if I took one of these out. Uh-oh. Okay. So let me change this And let me hook them up in parallel. Ooh, that's pretty hot.
Well, in parallel, the brightest one would be the one with the least resistance, which would be the 200 watt one.
Okay.
Because the voltage drops the same across all of them, right? Yeah.
That's right. The voltage drop is the same across all of them, but I got to do something first. Hold on a second. Why won't this work if I flip the switch?
Oh, because there's no. It's a shorted circuit, or not shorted. It's a broken circuit.
It's a broken circuit here
Yeah.
and here. In fact, every time I do this demo, I forget that. But since I did this now, because I did that happened to me on Wednesday. This time I remembered. Okay, I will stand behind here. 200 watts, pretty bright. Okay, so yeah, it's clear that the 200 watt bulb is the brightest.
Yeah, you can actually tell by the, like, how much red line you can see. Because on the camera, it just completely, like, overexposes it.
Yeah,
But you can still tell which one's brighter.
Yeah. Okay, so let me try something else. Let me put three of these bulbs in series. I'm going to put the 325 watt bulb in series, and I'm not going to short this out. So, I forgot to mention, there was every once in a while, and somebody might be thinking of this, but I'm going to bring it up anyway because there's always one person who thinks of it, somebody, and they bring it up. So going back to this demo, for some reason this bulb is hard to screw in. Somebody will always say, well, the reason why this one, I had these backwards. The reason why the 25 watt bulb is brighter is because they're in the wrong order. If you switch the order, then you'll see a difference in the results. And so then I do it for them, and they see that doesn't matter. The order does not matter here. Okay, but there's always folks who feel that the order matters here, but the current's the same through each one, so it doesn't matter. Okay, let me get some 25 watt bulbs here. Okay, and let me put 25 watt. So I'm going to have three 25 watt bulbs in series. Just give me a second. And you're going to see, and you see this effect when you do the multimeter quiz when the two bulbs are in series. So I turn them on. Of course, they're all on, but they're pretty dim, right? Because each one has 1/3 of the voltage. Each one has 40 volts across it. Suppose I take this 200 watt bulb and I screw into this socket. What happens?
Wouldn't it be brighter?
Which one's going to be brighter?
The 200 watt.
Okay. So if I put this in, so now look at how I've hooked it up. This is in parallel with this, right? These two are in parallel with each other.
It should be the brightest, shouldn't it? Because it has the least resistance of all the bulbs. Oh, they just don't light up.
Yeah, why? Why is that? In fact, these got brighter, right? These two got brighter. Here, let me take it out.
The currents split for the two in parallel, right?
These two are in parallel, correct, yeah.
So
Oh,
you have more current on that first bulb and then the last bulb. Well, you have the full current on the first bulb and the last bulb.
Yeah, and what happens, well, first of all, these two are in parallel. If you can replace these two with a single one, you look at this equation. When you add resistors this way, the result is smaller than either one of these two. Does that make sense? The equivalent resistance of two resistors in parallel is smaller than either one of the two. So my equivalent resistance is going to be smaller than the 200 watt bulb, the one for the 200 watt bulb. And this combination is in series with these two. And so what happens is then I have a small resistance here and two big resistance here. So they're going to have, remember, the current's going to be the same. The total current through these two is the same as the current through this guy or the current through that guy. And so they're going to have a smaller voltage drop. And that's why both of these get very dim.
Oh, so the total current of the system actually increases then?
Yeah, it does.
Because the resistance overall decreases because you added, yeah, okay.
You're right, it does. I mean, when I do this, what I'm doing is I'm increasing the total resistance. By putting these two in parallel, I'm actually decreasing the total resistance of the circuit. Okay? This simple little device, you can learn a lot from circuits. Just doing this with bulbs. Anybody want me to try anything else? Now, what happens if I take this one out? This one right here, what if I take this one out?
Well, the top bulb would be brighter in respect to the one you took out because it has less resistance, but it would be the same 3 in series configuration.
Yeah, so you still get the same thing, right? I mean, the values, it's true that the voltage drop will change a little bit, but not by enough. But what if I take this one out?
The circuit would just die.
Yeah, everything goes off. It's pretty warm. Because these are in series, right? You have no current can't go past this point. Anybody want me to try anything else?
If you do one on the top, they'll get brighter. Is that?
You want to put one up here? Yeah, the problem is because this one's so low. Maybe I'll take this out. Let me see what happens when I take this out. And really, it's because this one is so low. All right, if I had maybe another 25 watt, hold on a second. Let me put this down. I gotta reach across the room here. This is 25 watt. So let me put a 25 here. We don't notice much, do we? Even with these two 25s. Unfortunately, this is a different bulb. Hold on a second. Let me take that one out. The filament's different, so it's kind of hard to tell things. So here's a 25 watt. Okay, they all look the same now. And then let me put a 25 watt here. Wow, that's a big difference. And if I put something here, you're not going to really notice much of a difference. Because what happens is since these two have equivalent resistance, when I put these in parallel, this is going to be half. When I put the next one in, it'll be a third, but so you're not going to really notice much of a difference. Okay, so it's fun with light bulbs. Let me turn this off. So let me go through this example. I'm analyzing a circuit somewhat complex. Let me change my camera. Okay. So I want to look at this problem. And it does look imposing at first, but I'm going to do this, I'm going to do the same thing as what I did with the capacitor. I have this complicated network of, or fairly complicated network of resistors. What I want to do is find the equivalent resistance of the circuit. And then I want to find everything, the voltage across each one, the current through each one, and actually the power dissipated. Well, what's the first thing I can do?
Just add the two 12s together.
So I can add the two 12s together and replace them. So I would redraw the circuit. So 12 plus 12 is 24. Okay. Now what do I see? I see an 8 kilo ohm and a 24 kilo ohm in parallel. So I guess we'll do the math for that one. I have an 8 and a 24 in parallel. And actually the math isn't that bad. Now let me turn up the lights too. Okay. So to find the equivalent resistance, we have 1 over 8 plus 1 over 24. Common denominator is 24, right? Four over 24 is a sixth. So our equivalent is 6 kilo ohms. Sorry, my marker's dying. So it's 6 kilo ohms. So let's go back. Sorry, that's too faint. So I replace those two and redraw the circuit. Now I have 3 in series. I just add them. 5 plus 6 is 11. 11 plus 9 is 20. And so I redrew the circuit. And so the final circuit shows me the equivalent resistance of the whole thing. Now I'm going to work backwards. I'm going to find the current in my circuit. Well, finding the current in my circuit is going to be straightforward because I will use Ohm's law. I have 10 volts. (20 kilo ohms). So I is equal to delta V over R. And this gives me 0.5 milliamps. 5 times 10 to the minus 4 amps. Okay. So now I know the total current in my circuit. I have 5 milliamps going through my 20 kilo ohm resistor, but remember that 20 kilo ohm resistor is replacing the 3 that you see in series there. I do have half a milliamp and 10 volts, so I can calculate the power. Power is going to be 10 volts times half a milliamp. 10 times a half is what? 5? So I have 5 milliwatts of power that resistor is dissipating. So the battery is basically delivering 5 milliwatts of power and the resistors are using that all up. Now, let's take a look at the 3 resistors in series. Each resistor has half a milliamp. So half a milliamp times 5 is, what, 2.5 volts on the top battery. I'm sorry, the top resistor. 6 times a half is, isn't that 3? So we have 2.5, we have 3, and this one will be 4.5. And stop me if I'm going too fast. How do I calculate the power? Well, let's do this one. This one's simple. Half times 3 is what? 1.5? So 1.5 milliwatts here. Half times 2.5 is 1.25. And then half times 4.5 is 2.25. I did everything to 1 sig fig. If you add all these up, if you add the 1.2, the 1.5, and the 2.2, you should get the 5 milliwatts. It doesn't come out exactly because I was rounding off. Does that make sense? We're okay? Okay, I will go on then. Now, this kilo ohm resistor that you see here, remember, it replaced an 8 kilo ohm resistor and a 24 kilo ohm resistor, which were in parallel. Since they were in parallel, then the voltage across each of those 2 resistors will be 3 volts. And the current is going to be 3 volts over 8 kilo ohms. And for this one, 3 volts over 24. So 3 over 8 is 0.375. 3 over 24 is an eighth, 0.125. The sum of these two better equal to half an amp because that's how much current is going into this branch. And then power is going to be 3 times 0.38, and then 3 times 0.12. So 1.1 milliwatts and 1.36 milliwatts. Remember, on the previous slide, the sum of these two is about 1.5. We got to conserve energy. So these this 24 kilo ohm resistor replaced 2 that are in series. There were 2 12s. Those 2 12s will have the same current going through them. So basically the voltage is going to be split between them. So this is what we have so far. Each one of these 2 is going to have 0.12 milliamps going through them. The total will be 1.5 volts across them. So each one's going to have about 0.75. I'm sorry, each one's going to have 1.5 volts, sorry. Each one will have 0.12 milliamps going through them, and then the wattage is 0.36 milliwatts. And then for each one, it's 0.18. Questions on this one? So these don't seem too complicated, I'm hoping. Because you're not asking questions. So let me do something more complicated. Obviously, I'm going to do something more complicated. Well, let me go back. So there's actually 2 problems here. A Wheatstone bridge is actually used to measure resistance. So what I want to know is, if I hook up this circuit, what are the conditions on the resistors so that no current goes through the ammeter. We have to assume that the ammeter is idealized. What does that mean, that the ammeter is idealized?
It has no resistance. Wait.
Yes.
Yeah, okay.
Yeah, it has no resistance, so there's no voltage drop across the ammeter. Okay, so what does that do for us? Let me draw the circuit.
Wait, so then the bottom two resistors have to be equal resistance, right?
Not necessarily.
Well, because then no charge would flow across the wire. The
I mean,
ammeter.
it does. I mean, that's one possibility, but it's not as general as. There's actually a more general relationship that we can derive from it. Now, in that label, 0.1 and 0.2, isn't it true that since the ammeter has no resistance, that the voltage at 0.1 and the voltage at 0.2 are the same?
Yes.
Okay, so that's our first condition. Our second condition is that all the current going through RA has to go through RC, because nothing's going through the ammeter. Whatever goes through the top resistor, RA, has to go through the bottom resistor, because it's not going to go through the ammeter. Does that make sense?
Yeah.
Okay. Okay, so R sub A, R sub B, R sub C, so this is 0.1, this is 0.2. So we know that V, this is the actual potential, not the potential difference. This point and this point are at the same voltage. And, oh, this is A, sorry. If no current flows through the meter, then the current through A has to be equal to the current through C. They're in series, basically. That's what that means, right? And I sub B has to be equal to I sub D. If this point and this point are at the same potential, and of course up here, this is the battery voltage, then the voltage drop across this point and the voltage drop across these 2 points are the same. So I can say then that delta V sub B has to be equal to delta V sub A. The currents don't have to be the same. Right, because Andrew, you're saying the currents have to be the same through the, but they don't have to be. But the product of I sub B, R sub B has to be equal to I sub A, R sub A. And then we can do the bottom part if these 2 points are the same potential. And then, of course, for RC and RCB, they both have this point in common. Then delta V sub D equals delta V sub C. And so I can say I sub D, R sub D equals R sub C, I'm sorry, I sub C, R sub C. Okay, what I'm going to do is set up. You guys okay with me erasing this? I hope. So let me write these equations again. Now, we said that IA equals IC, so let me replace this with a A. And IB equals ID, so we replace this with a B. And now divide equations. As long as the resistors satisfy that condition, you'll have no current going through the ammeter. This is the Wheatstone bridge. And so generally what happens is when you do a Wheatstone bridge measurement, you put an unknown here, and you put two known resistor values here, and then this one you can vary. And you vary the resistor until no current goes through here, and then you can calculate what that unknown is. Of course, you have to worry about the resistance of the meter. That's the source of error. So you basically want the resistance of the meter to be way lower than any of the resistors you're measuring. Are we okay with that?
Question.
Yeah.
How do we figure out that delta V of B is equal to the delta V of A and delta V of C equals delta V of D?
Because these 2 points are in common for these two resistors. Isn't that true?
Yeah.
So they have the same V.
Oh, and V1 equals V2.
Yeah, so that means this difference, the difference between these 2 points and the difference between these 2 points have to be the same.
Got it. Thank you.
And then this is what's left over, so these two have to be equal. So now I'm going to do one where the bridge is not balanced. Okay, let me do one where the bridge is not balanced. So let me make the battery voltage 300 volts. Let me make this 3 kilo ohms. Let me make this 6 kilo ohms. So this is not a balanced bridge. Okay, so C is 2 kilo ohms. And then D is 2 kilo ohms. So if you apply this condition, you'll see that the right-hand side is not equal to the left-hand side. Okay? So this is not a balanced bridge. So current will go through the meter. So in this case, not equal to 0. So what is it? What is the current going through there? That's the question. So these 2 points are at the same potential, isn't it true? And of course, this is in common. The meter itself forces 0.1 and 0.2 to be at the same potential. So I'm going to redraw the circuit for you. Let me see if my purple is working still. Okay, I'm going to draw it in purple. I'm going to redraw the circuit. The same thing. Isn't that the same circuit?
Yep.
Okay, so because this has no resistance, these 2 points are at the same potential. In fact, I can draw it this way. Represents the same circuit. Sorry, I've gone so far low on this thing. That's the same circuit. Now, can I replace these two with equivalent resistor? They're in parallel. 1/2 plus 1/2 is what? 1. What's the reciprocal of 1? 1. So basically what I have, oh, I got to replace these two. When I replace these two, what do I get?
Two.
2.
Right.
Did everybody see you get 2? Okay, so this is 300 volts. So I have 300 volts or over 3 kilo ohms, which is 0.3 amps. I'm sorry, 0.1 amps. 300 over 3,000. Yeah, 0.1 amps. So I have 0.1 amps going through each point here and here. So I have 0.1 amps going through these two. So what's the voltage drop across? What's the voltage drop across that 2 kilo ohm resistor? What's 2,000 times 0.1?
200.
200. And this one is 200 volts, right? 100. I need to make sure you can see that. You guys can see that, right?
Yeah.
Okay. So these two are in parallel, so that means they both have 200 volts across them. So how much current is going through this guy? Well, I got to take 200 divided by 3,000. Which is 33.3 milliamps. Yes. And this is 66.7 milliamps. So let me draw in my circuit here. I have 33.3 milliamps. Can you see that green okay? Or is it too light?
It's good.
Okay. And this is 66.7 milliamps. So here I have, each one of these is at 100 volts. Guess how much current goes through these ones? I take 100 divided by 2,000, that's 0.05 amps, or 50 milliamps. So I have 50 milliamps here. So what happens? Let's look. The current's going this way. Current comes this way. I have 66 here, 50 here. Where does the rest go? right? I hit this junction. I have 66 milliamps going here, or 66.7. I have 50 milliamps going here. 16.7 has to go this way. Doesn't that make sense?
Yeah, just a difference.
I'm sorry?
Just a difference, right?
It's just a difference, yeah. Because charge is conserved, right? Because whatever goes into a node has to be equal to whatever comes out. So I have 66 going here. These two add up to 66. Now let's go to this side. I have 33 here. I have 50 here. Where's the missing stuff come from? Well, it comes from this guy. So these two come into the junction, and then they come back, and then the current comes back down this way to 50 milliamps. And so the meter will tell you the current's going that way, and then coming down here. So the next lab you're going to be doing, you're going to analyze this circuit, and you're going to actually make measurements to verify this. Okay? So this is essentially your next lab, which will come in a couple of weeks. And so you're going to make all the measurements that's required. You're not going to be measuring current in each branch because you would need like 4 ammeters. But we have a way to get around that. Are we okay? Everyone's quiet. I'm sorry?
Just one question.
Yeah.
Bottom right, how do we find the current?
I'm sorry, say that again.
Bottom right, the circuit that only has 2 resistors.
This
How do
one?
we find the current? Yeah.
How did I find the total current?
I got it, because we find the resistors, and then the current is constant across the series. Got it.
Okay, all right. That's fine. I want to make sure it's clear. So I think right now it's about 1220. So I'll do this example. This is a fun one for you guys to think about. So when we come back from our break, we'll take a 20-minute break. We'll meet at 12:40. And I will go through this example. And I'll talk about a couple other things, and then we'll start about Kirchhoff's laws. Okay? So I'm going to eat something over the next 20 minutes, and I suggest you do the same thing. All right, so we'll take a break here.